Hello everyone, in this video we are going to be solving this integral over here whilst also learning the technique U substitution, or U sub for short. You can think about it sort of like the inverse chain rule. So I've also introduced bounds. I talked about this before. They're essentially limits for our integral. We never really explored the geometric interpretation of an integral, but essentially what it is it's the area under the curve. So let's say this is the line y equals x, right? The area sort of under, quote unquote, under the curve or bounded by the x-axis, and the function would be like this area here. So the integral of x dx is equal to the area. Okay, so if I say the integral from 0 to 2, it just means from 0 to 2 only. So forget all of that stuff. It's just this area. So this is why this is even helpful in contest math, especially with triangles or even circles. You can solve area problems much faster. But anyways, the reason I wanted to introduce it now is because with U substitution, it influences those bounds, and I didn't want to sort of get you guys caught up later. So how do we solve this problem? Well, I want you to notice the two functions that we have. We have 1 over x squared plus 1, and we have x. If I were to differentiate this function over here, right, what would I get? Because at the end of the day, an integral is just the opposite of the derivative, okay? So I want to think, when I differentiate some function, it's equal to this function. Right? In other words, y prime is equal to x squared plus 1, right? That's all I'm thinking about. When I differentiate this, I'm going to get 1 over x squared plus 1 quantity squared negative multiplied by the derivative of the inside, which is 2x. You'll notice that is pretty close to what we have over there already, right? Minus a couple details. But anyway, that's sort of what I just wanted to get going right now. So let's start. I have x squared here. I know the derivative of x squared plus 1. So I'm going to set this equal to u, because, I don't really know how to deal with something like this right now. Now, we are in luck because 2x is the derivative of x squared plus 1. You'll notice I'm saying that 2x dx is equal to du. We have an x dx right here. You don't have the 2, so we can just divide both sides by 2. No problem. Now what we can do is say that this is equal to du over u, right? This is u, this is du over 2. It's perfect. It's perfect. I'm going to just take the half out. Okay, last thing, the bounds. What happens to the bounds? We are going to take the limit as x approaches 0 of our function. So let's see, we said this, right? Which means we're going to take this limit over here. And that's just going to give us 1, which means that our lower bound is going to be 1. Now, let's take the limit as x approaches 2 of x squared plus 1. We're just going to get 5. Upper bound is 5. Okay, we know that this is just going to be ln u, and this notation is called like sort of evaluated at. If we, I'm just going to do brackets because it's easier. But if you do see that other notation, know that it's just the same thing. It just means, all it means is this: ln 5 minus ln 1 It's just the upper bound minus the lower bound, basically. We know ln1 is 0. So the final answer is this. Or if you want to be cool, you can write it like that too. Now you might have noticed our final answer did not include a plus c. That is because in a definite integral, you don't need plus c, because I told you, it's the actual area underneath the graph, right? It's the actual area. It's not the antiderivative, which is what we've sort of been doing before. The antiderivative is half ln u plus c, where we can replace u with x squared plus 1, right? If we were to differentiate this, we would get half 1 over x squared plus 1 multiplied by the derivative of x squared plus 1, which is 2x. You can see we get the thing. So when you're doing u sub, it's often because you see a function and its derivative. Now that's, if you're lucky, most cases it's actually more complicated than that. But in the basic case, this is sort of the premises of using it. Another premise is if you're just trapped, like how are you going to deal with this, right? Someone more experienced could use integration by parts to solve this, but we haven't learned 1 over x squared plus 1 just yet. Which is why I encourage you guys to just go online and search up what are all the common derivatives and antiderivatives for all the common special functions: sine x, cos x, tan x, and then of course arcsine, arccos, arctan, exponential, logarithmic, and power rule. All of those. Just know all of those for next video, or just have like the Google sheet out. That way we don't have to keep referring to it, because I don't want to have you guys just, memorize that for an entire thing, okay? So I'll see you then.